naye olunaku olwaleero olw'enteekateeka eriwo eya misa eya Good Friday Rubaga tugenda kuba butereevu tubanamu era nga ku ssaawa eno Master Mugaya yazze dda ava ku Maryland agenda kubatwala mu ssomo lya Pure Math. Banaffe atuteekamu ssente Maryland High School, banaffe aba Gwini Schools ate wamu ne BIC twebaza nnyo mwebayi ddala ko n'Enkumba University. Katono nnyo ku bigenda maaso mu ggwanga e Congo abantu beeyongedde okufuna obulwadde buno bwa COVID-19 ku makya babadde bali 108 bokka kakati Congo ekyasinze okuba n'abalwadde abangi mu Africa ekyasinze okuba n'abalwadde abangi mu East Africa mawanga gano agatulinaanye kati ng'eyina 215 ate nga n'omuwendo gw'abafudde gweyongeddeko kati awezezza 20. Awo nno embeera si nnungi, eggwanga lya Congo lino lizze lisenvula mpola kati laba gye lituuse abantu 215. Butereevu njagala kwase musomesa abeere nga tutwala mu ssomo lya Pure Mathematics olwakadde era mbagaliza kiraasi ennungi.
Thank you. I want to welcome you. Draw closer with your pen and where you're going to write, so that we get to business. Again, your facilitator today is Mugaya Samson. For the few times we've been interacting, we've been looking at integration. We looked at some techniques of integration. And today we want to touch some very important application of integration. Dear viewer, one way you're going to benefit from these sessions are only intended to kickstart you off. The person who is really going to be doing a lot of personal revision is the one who is going to benefit deeply. Here we are able to touch a few things to kickstart you off so that you can do personal reading. So you need to have that personal initiative. That's why sometimes you'll see a few things being left out here and there. You need to follow up and do a lot of reading. Today we are going to talk about, or we are going to discuss, differential equations. It's an application of integration. Differential equations are very, 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 very important. In fact, for most of you who are going to have an opportunity to pursue mathematics up to very high levels, you realize that almost life is summarized into equations, differential equations. In technology, in the medical areas, you're going to be meeting differential equations. In economics, you'll find differential equations. So solving differential equations is really, really very important. Even these aeroplanes you see flying, they are just equations. Someone had to solve some differential equation called the Navier-Stokes differential equation, and then it led to that upsurge of aerotechnology. So in life, you're going to meet differential equations so much. So today, I want to introduce you to differential equations as an application of integration. What is a differential equation? Sometimes I'll be writing the E to mean differential equations. So one, we need to define it. What is a differential equation? It is an equation involving at least one derivative. So if you meet an equation, when it has at least one derivative or a differential coefficient in it, then you'll be right to call it a differential equation. For example, if we have dy by dx equals to 3x, that's a dE. Let's call it 1. If we have maybe d2y dx squared plus 2x dy by dx, maybe the power 4 equals to 0. That's also a differential equation. d3y dx cubed plus y equals to 0. All those are examples of differential equation. Just write an equation, insert somewhere a differential coefficient, you got yourself a differential equation. differential equations, there are very many types of differential equations. There are those which are ordinary, then there are those which are partial. At our level, we talk mostly about the ordinary differential equations. What you need to know, maybe, is the order of a differential equation. Again, I said the moment you see the E, I'll be applying differential equation. So the order of the E, this is simply the order of the highest derivative. It's the order of the highest derivative or the highest differential coefficient in the equation. So if I want to know the order of a differential equation, all I need to do is to look for the highest differential coefficient in the differential equation, and that will be the order of the differential equation. For example, here, this is the highest derivative, and it's of order 1. It's a first derivative. And so 1 is a first order what? A first order differential equation, and it's ordinary. Then 2, this one here, the highest derivative is this second derivative, and so 2 is a second order. Second order ordinary differential equation. And then, of course, 3, that one you can guess. So that is the order of a differential equation. How do we form differential equations? Of course, differential equations arise from a number of situations in life. However, here, in forming a differential equation, I just want to show you how you can begin with a general expression and you form a differential equation from it. So forming a dE. These are very important introductory bits. Forming a dE. If an expression maybe contains n arbitrary constants, if you want to form a differential equation from that expression, you differentiate n times, of course. You differentiate n times, and you use mathematical manipulation to eliminate all the arbitrary what? All the arbitrary constants. What will come out will be a differential equation, and the expression you differentiated, we call it a general solution for that differential equation. For example, mathematics is better understood with examples. Form a dE by eliminating A and B. So we are assuming A and B are arbitrary constants. Y is going to be ax squared plus B, and then B, y equals to A, E, bx. So we want to form differential equations from those expressions, or we want to form differential equations whereby these expressions are solutions to those differential equations. So since we have two arbitrary constants, then we are going to have to differentiate 2 times. So in our solution for part A, we have y is equal to ax squared plus b. So we differentiate the first time, dy dx is equal to, when you differentiate this, you'll have 2ax plus 0. We know the general rule. When you differentiate a constant, you get 0. Then we still have one more arbitrary constant there. We have to differentiate again. Dy dx, this is now the second derivative, the 2y dx squared. This is going to be 2a. And to do away totally with that, we get the 3y dx cubed is going to be equal to 0. So this is the differential equation, which is arising from that. Some expressions may not be so easy. You may need to make things the subject somewhere, and then you have to put in some skills of eliminating the constants. If you have two arbitrary constants, you will need to differentiate around 3 times. If you have n, around n plus 1 times. And so I don't want you to be dormant, dear viewer, so part B should be an easy exercise for the viewer. With that done now, we want to get to the normal business, because our interest, or why we are interested in studying differential equations, is because we want to learn to solve them. There are people today in the world who are doing PhDs in just trying to learn how to solve one kind of differential equation. So solving is the most important thing. What does it mean to solve a differential equation? Or when do you say that you have solved a differential equation? That is if you have managed to eliminate all derivatives in the equation, and that is only done by integrating. That is undoing the differentiation process which led to the differential coefficients. When you eliminate the derivatives, or by integration, you're solving the dE, and we expect 2 kinds of solutions. We can expect 2 kinds of solutions. There is what we call a general solution, and this one involves arbitrary constants. It involves arbitrary constants. For example, if we have solve dy by dx equals to 2x, we made that in integration. We are just asking you to find the function y such that when you differentiate it, you get 2x. And so all we are going to do is integrate both sides with respect to x. So we shall have integral of dy by dx, but with respect to x. This is going to be equal to integral of 2x with respect to x. When you integrate that, you'll get y, and you integrate this, you'll get x squared plus an arbitrary constant. So we say that this guy here is a general solution to that differential equation. So this guy is a general solution. Why? He has an arbitrary constant. In other words, he represents a family of solutions. A can be any constant. So this actually is representing a family of all functions of that form. You can put any constant in that place. It will satisfy that differential equation. A can even be 0. Then there are times when we obtain what we call particular solutions. Particular solutions. These are only obtained when we are given initial what? Obtained when given what we call initial conditions. This one is representing a family of solutions, but this one is particular. In other words, there is extra information which you're going to be added, more specific information, and that information is now no longer satisfied by the family, but rather it is satisfied by only one guy in the family. And that is the guy we'll be looking for. So that's the one we are calling a particular solution. So for example, if here we had the additional information that y maybe is 1 when x is 0, then we would have to come back to our general solution. We substitute in to find the constant a. So we will say y is going to be 0 squared plus a, which means that a is going to be 1. And therefore, we have a particular solution, that is y is equal to x squared plus 1. So in this family here, there is only one guy, this one here, who can satisfy that condition and then this condition. So these are the conditions we are calling initial conditions. So when you're given initial conditions, we expect to get a particular solution. Now, differential equations are very wide. In fact,